Hello everybody and welcome to our webinar. My name is Vladimir Podnos. I'm Director of Marketing Support, and I will introduce my colleague Sergey Yonin, who will continue about basics of our thermal problem setup. So, what thermal problems are available in QuickField and how to set them up? QuickField has a variety of analysis modules, and it includes magnetic analysis suite, electric analysis suite, and thermostructural analysis suite. Today we will concentrate our discussion around steady-state heat transfer and transient heat transfer. And stages of solution of heat problem in QuickField are generally the same as for any other types of analysis. You should define your geometry, specify physical parameters, and then you may analyze your results using color graphics, plots, and local value display. What is specific for thermal analysis? The thermal parameters which should be defined for blocks should include thermal conductivity, volume power of heat source, and for transient problems, specific heat and volume density. On edges, you may specify temperatures, fluxes, convection or radiation boundary conditions. It is also possible to define equal temperature on edges and even or odd periodic temperature. On vertices, you may specify first order boundary conditions like temperature or local heat sources. It is also possible to couple thermal problem to electromagnetic problem and transfer Joule heat distribution from electromagnetics, from electric problems or from magnetic problems. Usually, most complicated part of thermal analysis is selection and setting the boundary conditions. And today we will speak more about convection and radiation boundary conditions.
Hello dear colleagues, my name is Sergey Yonin and I'm a QuickField support engineer. And today we will learn basics of the thermal problem setup. Four types of problems will be reviewed today. First is heat transfer to the wall and heat loss calculations. Second is the nature of convection problem with calculation of convection coefficient. Third problem is a radiation problem. It's a heat transfer in case of radiation. And problem number 4 is a complex problem with automation. Let's go to the first problem. On the screen you can see the wall of a steel tank that contains hot water at a temperature of 95 degrees Celsius. Ambient air temperature is 15 degrees Celsius. The task is to find the heat flux flowing through the wall and the outside wall temperature. Convection coefficients and thermal conductivities are given. This problem is very simple, and the solution is published in the book. It's a Rushwood book. We selected for the demonstration of the QuickField general workflow. Now let's run the QuickField and create a new problem. That's a QuickField. And I'm creating a new problem. Let's call it heat transfer. Let's transfer. I press the button finish. Now I should create a geometry. Actually, I'm drawing the wall, and the shape of the wall remains the same as the wall height of the wall, so that we may draw just a little piece of the wall, meter 1 by 1 meter, and the width is 12 millimeters. It's wall 1 meter high. and I duplicate this edge by displacement on 12 millimeters. Then I should bring this vertices and on the bottom. And the wall is ready. But it's not the now it's not the wall, but just a block. Let's name it. Let's call it wall. And we should set the properties of this wall. Just the state problem, and we should set just the geometry. It's enough. Also, I should set the boundary conditions on the edges. On the left edge, I'm gonna have the water. Means that this edge, the surface is hotter. And on the right, I'm gonna have the air side. And now I set my properties. Convection for water and for the that's conduction equation for the water side for the temperature of this water in Kelvin, 95 degrees Celsius. And for the air, convection equation is 10, and the temperature in Kelvin is 15 degrees Celsius. Okay. Now I should automatically generate the mesh and solve the problem. And solution is back. First, let's look how the heat flux flows through the wall. I press build picture properties and display vectors of heat flux. As you can see, they goes from the left side of the wall to the right, from the heat area to the cooler area. According to the conditions, we should calculate surface temperature on the air side. Let's calculate it. Surface temperature, and also we should calculate heat flux. And let's compare our results with the analytical one. Fury and also, we can change our problem. I mean, the conditions problem. For example, I can divide my wall on two parts like this. I can take this edge and duplicate to the a little bit to this edge. I divide my wall to set different materials on the left side and on the right side. Let's look here. Let's here. That's very good. Okay, and then I check. So this. Now it's external strong parts of the wall, and I will call it insulation, because this part will be insulated, and this part remains the wall with the same properties as in the previous settings. And for the insulation, I set a very low thermal conductivity, for example 0.5 watts per Kelvin meters, and press OK. Now we should generate the mesh again. On each block, of course. That's strange. Oops. Solution ready. As you can see, the solution changes radically. Now, the temperature distribution is not it's not uniform at all, like in previous sets. And I can show you the plot of the temperature distribution, and it's a very rapid drop of the temperature in the insulation block. And also I can calculate heat flux passing through the wall. Volume, as you can see, it's reduced very much. Okay, so we have solved the first problem, and now let's consider a second problem. It's devoted to the nature of convection and calculation of the convection coefficient. The initial problem is a brick wall covered with thermal insulation and the plaster layers outside. This yellow layer is insulation, and this blue is a plaster. Dimensions of the layer are given. Temperature inside is plus 20 degrees Celsius, and outside temperature is minus 10 degrees. Thermal conductivities of materials are given. Our goal is to calculate the temperature distribution inside the wall. The wall is cooled by the outside air and heated up by the room air. In the previous problem, convection coefficients were given. Now they are not. It's impossible to solve the problem without these convection coefficients. Convection coefficient depends on many properties, many things. But not first, but it depends on the surface, shape and orientation, and a lot of properties of medium. For example, it's a viscosity. In our case, it's viscosity of the air, thermal conductivity, density, channel coefficient of volumetric expansion, heat capacity, temperature difference. Well, to calculate this coefficient, the difficult problem of gas dynamics, including air diffusion and the mass and heat transfer, should be solved. But for the reasonable engineering accuracy, it's enough to use empirical formulas based on the similarity theory of heat transfer. That's formulas. Our case is a vertical wall, and the formulas for the similarity numbers of Grashof, that's a Grashof number, Prandtl number, Rayleigh, and then Nusselt numbers are known. As you can see, these similarity numbers depends on properties and geometric parameters of the system. And if the Nusselt number is known, we can calculate the convection coefficient. Okay, and let's take a look at the settings now. I close previous problem. And let's do this one. And I open my problem finally. And that's my geometry. Indeed, there's 3 layers here. It's a brick with the relevant channel connectivity set in the properties. Also, I have an insulation. It's a pretty good insulation, as you can see. And the very thin layer for plaster. That's plaster with thermal conductivity, of course. Also, I should set the properties on the edges. On the cold side is the rightmost edge of my model. Here's the convection coefficients and the temperature. And also, I have the convection boundary conditions on the room side. By the way, I'd like to show you how we calculate. That's my similarity theory numbers, Brownsville numbers, Garfield, Rayleigh, and Nusselt, and the convection coefficient. So I just want to prove you that the convection coefficients were calculated accurately. And after this calculation, we have the complex settings for the problem. And now, let's solve this problem. Let's press this button. The solution is ready. And that's my temperature field. Let's draw the contour through this wall and display the distribution. By the way, this problem can be very helpful in one aspect of civil design. I mean the calculation of dew point. Dew point is a region where the where the air is condensate. Means that it will be a area with some amount of the little amount of water. But typically it's about 10 degrees, and temperature of 10 degrees Celsius will be in the insulation layer. In kelvins it will be 283 degrees Kelvin. Also, we can calculate heat flux passing through the wall. I press this button, integral calculator. I will calculate heat flux. It's a pretty low value to compare with the value from the previous problem. Okay. So we have solved the problem. And let's go to solve the third. And the problem number 1 and number 2, the temperatures were rather low. But sometimes temperatures in the heat transfer problem are very high, and in this case we should take into consideration another way of heat transfer, another mechanism. It's radiation, and third problem is devoted to the radiation. Let's take a look. It's an incandescent light bulb. Our goal is to calculate temperature of the filament. The filament is made of tungsten. Typically, it's made of this material. So you may wonder how we can do this, because the tungsten filament is twisted into a spiral, like here, this. But that's not a very big problem for us. Filament is twisted, so only one side radiates outside. That's a few loop of tungsten filament, and you can see that only the outside, only the one part of the surface radiates outside. The other side radiates inside the filament itself. That means that there is no heat exchange. And after the strengthening of the tungsten filament, we will get very simple settings. And in terms of boundary conditions, we should divide our block. It's a plain parallel problem. And we should divide this block on two parts and set zero flux boundary conditions on the bottom part, and we should set radiating conditions on the rest part. And as heat sources, we set volume. We set volume power of the lamp here. We have the bulb power. In our case, it's 100 watts, and we divide it on the filament volume, and we get the volume of volume power. So let's see the settings in the QuickField. I close the problem again. And I open the third folder. That's the geometry. As you can see, it's very simple. Let's take a look at the settings. Okay. This is a tungsten filament, the thermal conductivity and volume power of heat source set. And also, there's two edge labels. So let's see that. Bottom surface, I set the heat flux equals to 0. As in the presentation, so I'll explain. And on the top surface, that's top surface, I set the radiation boundary condition, where beta is the emissivity coefficient, 0.39. It's this coefficient is less than 1 always, and its temperature is the temperature of the ambient air. In Celsius, it's 20 degrees. And I press OK. Now let's solve this problem. That's the temperature field. Temperature is It doesn't change inside the contour. And our task is to calculate the average temperature of the filament. I press the button, and that's my temperature. It's about 2400 kelvins. Usually the filament temperature lays within 1800 to 2700. Okay. So the last problem of our webinar is devoted to the optimization utility of the QuickField called label mover. The problem is the following. Hot steam is passing through a steel pipe. This orange is a steel pipe, and the steam is passing through this. Also, this steel pipe is insulated by the asbestos, and our task is to calculate the outer radius of the insulation, or thickness of the insulation layer, which provides the range of heat losses of 2100 watts. On the inner and the outer surface, the convection boundary conditions are set with the temperatures and kelvins. And also the thermal conductivities of the steel and the insulation are known. So let's go to QuickField and see the settings. That's my geometry. It's still. Now it's displayed. And that's asbestos. Now thermal conductivities are set here, of course. Also I have the edge labels inside. Convection boundary conditions are set here. It's a 150 degrees. It's the temperature of steam. And the convection coefficient is also set. It's pretty big. And also I have the convection boundary conditions on the outside edge. 20 degrees Celsius is the temperature of the ambient air, and the convection coefficient is 30. So let's solve the problem for the natural conditions. The temperature distribution. Let's calculate the heat flux passing through the pipe. That's my volume. Minus means that the heat flux was passing outside. According to the requirements, we should increase this volume. Let's try to do this. I select this button, parametric analysis with label mover. Label mover can do a lot of things. I'm interested in optimization today. But first, every optimization problem required setting of a call function. I didn't tell you that I have one edge label that is called arc_x. That's just a surface actually that divides my pipe on steel sides, on the steel part and the insulation part. And the heat flux is passing through this surface as through each of the surface. Okay, and I'd like to set the heat flux close to minus 2100. It means that the heat flux passing through the cylindrical surface divided by this by this edge is should be close to 2100, and I add this go function. Also, I should add variations. It means that I should change something in my problem. I will scale the outside edge. The type of variation is the geometric variation. Method scaling, as the factor will be within 0.5 and 2. And I select outside and press add. Okay. And now I can do notation. On the 0 step, QuickField solved the problem for the initial conditions, and that's a value that I have already shown you. On first step, QuickField increase the radius of the outside edge, and it leads to the reduction of heat flux, but it's contrary to our task. And on the second step, the scale factor reduced it, and it's now less than 1. Means that the outer radius of the insulation reduced. And on step number 7, QuickField found the best solution, very close to the goal function of 2100. Let's take a look at the settings of this problem. That's my new geometry. As you can see, the insulation layer became thinner, and that's my new radius. That's about 104 millimeters. And let's make sure that the heat flux is about 2100. Let's calculate heat flux. That is about 2100. By the way, this problem, not all of this problem, but the convection coefficient from the outside surface of a cylinder could be calculated using a similarity theory. We can simply calculate Grascoff, Parental, Rayleigh, and Nusselt numbers, like in problem number 2, and calculate the convection coefficient after this. And for more thermal examples and for more other examples, visit our website quickfield.com and link to applications, industrial, wait for a minute. That's the industrial applications list. And the thermal models among these types. And that's a lot of thermal examples.